You want to buy photographic paper to print this photo in two different sizes. So these are the two different sizes in which you want to print this photo in. You know that these two different sizes are, this small photo is 6 by 10 inches and this larger one is 18 inches by 30 inches. Now you know the price of this small paper which you want to print this image on. What would be a reasonable price for the larger paper? So you know that the 6 by 10 inch paper costs 30 rupees. So that is, if area is 60 inch square, then the cost is 30. Cost is dependent on the area. More the area, more would be the cost. Now, you want to find the cost of this larger sheet, which is 18 by 30 inches. So if it's 18 by 30 inches, that is 540 inch square. Now you want to find the cost of this. Applying unitary method, you know 60 inches cost you 30 rupees. So 1 inch would cost 30 by 60. Similarly, 540 inch square would cost 30 by 60 into 540. So if I solve this now, I see that the cost becomes, for a 6 by 10 inch paper, the cost was 30. For 18 by 30 inches, the cost becomes 9 times the cost. That is 9 times 30. The cost has increased by 9 times. So we see, these are the two papers which you want, 6 by 10 and 18 by 30. Do you see that any relation between the sides of these two sheets? 6, 18, 10, 30. You can see that the sides of this have increased or scaled up by a factor of 3. These two are actually similar figures which have been scaled up by a factor of 3. So 6 into 3, 18, 10 into 3, 30. So the sides have increased by a factor of 3. And what about the area? Area is here 6 into 10, 60. Here area is 18 into 30, which is 540. So that is 60, and this would be, if I compare it to 60, this would be 540 can be written as 9 into 60. So here I have 60. Here it is 9 times 60. So area, sides increased by a factor of 3 and area increased by a factor of 9, which is square of 3. So the area increased by a factor of 3 square. So since the area increased by a factor of 3 square, which is 9, the cost is a function of area. So that is why the cost also increased by a factor of 9 and it became 9 times 30. So now we've seen that in similar figures, we've seen two similar figures in which if sides are increased by some factor, the area is also increasing by square of that factor. What about similar triangles? Can I apply this to similar triangles? Let's say I have these two triangles. I scale this larger triangle, I increase it by a factor of 3. So what about the area? Would the area increase by a factor of 3 square? Can I say that? Let us try to find that now. So now let us try to find the area of these two similar triangles. I know that what I am given is that ABC is similar to triangle DEF. So these are the two similar triangles. How do I start my proof? Let's draw a perpendicular. ABC, I draw a perpendicular AL. So this is the perpendicular and I call this point as L, which meets BC. Similarly for triangle DEF, I draw a perpendicular and call this point as M. So I get AL perpendicular to BC and DM perpendicular to EF. Now I know that these two triangles are similar. If triangles are similar, corresponding angles are equal. So B is equal to E, A is equal to D and C is equal to F. Also, ratio of the corresponding sides is proportional. That is, AB by DE would be equal to BC by EF, which is equal to AC by DF. So I get that the ratio of the sides is also equal. So now, let us look at these two triangles, ALB and triangle DME. In these two triangles, I know that angle ALB and angle DME is 90 degrees each, because DM is perpendicular to EF and AL is perpendicular to BC. So I know that this angle is 90 degrees each and angle B is equal to angle E. This is what we are given. Angle B is equal to angle E. So I have these two things. ALB equals to DME. I constructed AL and DM in such a way that they are perpendicular to BC and EF. And B is equal to E, which is given. Now, two angles of this triangle are equal to two angles of this triangle. So when two angles of one are equal to two angles of the other triangle, I can say that the triangles are similar by angle-angle criterion. So what I can say is that these two triangles are similar. If triangles are similar, then the corresponding ratios of the sides would be equal. So let us take the ratio here. So AL by DM. AL by DM would be equal to AB by DE. That is AB by DE. So this is what I get. AL by DM is equal to AB by DE. But I already know that AB by DE is equal to BC by EF, which is equal to AC by DF. AB by DE, AB by DE is equal to BC by EF, which is equal to AC by DF. Now I also get that AB by DE is equal to AL by DM. So clubbing these two, I can say that ratio of the corresponding sides is also equal to AL by DM. So I get this. So this is what you need to remember. What I find is that whenever you have two similar triangles, not just the ratio of the corresponding sides is equal, but the ratio of the corresponding altitude is also equal. AL is an altitude in triangle ABC and DM is the altitude in triangle DEF. So we see that the ratio of the corresponding sides is equal to the ratio of the corresponding altitudes, AL by DM. So this is what you need to remember. So we have this ratio of corresponding sides equal to the ratio of the corresponding altitude. Now let us try and find the area of triangle ABC. What would be the area of this triangle? Half into base into height. If I take BC as my base, then opposite vertex to BC is A. This is the height. So I get that area would be half into base into height. Base is BC, height is AL. So half into BC into AL. Similarly, I can find area of this triangle also. Area of this triangle would be half into base, which would be EF, into height, which would be DM. So half EF into DM. Now if I divide these two, if I divide area of triangle ABC by area of triangle DEF, then I'll say that I'll divide half BC into AL by half EF into DM. What is common is only half. So what I'm left with is, so if I divide the two, this is what I'm left with. Now I know that AL by DM is equal to AC by DF, which is equal to BC by EF, which is equal to AB by DE. AL by DM is equal to the ratio of the corresponding sides. So instead of AL by DM, what I can do is, I can write any of these sides. So let's say I write BC by EF. I'll say that AL by DM is equal to BC by EF. So this is what I get. Instead of AL by DM, I write BC by EF. So BC by EF into BC by EF. So area of this triangle divided by area of this triangle is BC by EF into BC by EF. So this can be written as BC square by EF square. BC into BC, BC square, EF into EF, EF square. So we see that ratio of areas of these two triangles actually comes out to ratio of squares of sides of these two triangles. Now we know, so this is again what you need to remember. Now we know that these two triangles are similar. So if triangles are similar, then the corresponding sides are also proportional. So I can say that the corresponding sides are proportional. If corresponding sides are proportional, squaring each, I know BC square by EF square would be equal to AB square by DE square. This would be equal to AC square by DF square. So what I do is I square each. So squaring I would get this BC square by EF square is equal to AB square by DE square is equal to AC square by DF square. Now this is what I get. Also I know I just found that area of this triangle by area of this triangle was actually equal to BC square by EF square. But now BC by EF square, BC square by EF square is actually equal to this entire expression. So I can say that area of triangle ABC by area of triangle DEF is equal to either this or this or this. That is, area of triangle ABC by area of triangle DEF is actually square of the corresponding ratios. So ratio of the area turns out to be square of the ratio of the corresponding sides. So this is what you need to remember. And we can say that the ratio of areas of two similar triangles is equal to the square of the ratio of the corresponding sides. So now, if I come back to the previous question. Now I increased the sides by a factor of 3. So the area would increase by a factor of 3 square, which is 9. So if area here is, let's say, small letter A, if area is represented by this letter A, then what would be the area of this larger triangle? 9 times the smaller triangle, that is 9 times A, which would be 9A. So we see that area increases by square of the factor in which the sides increase. Also remember that if the two triangles are similar, then the ratio of corresponding sides is actually equal to the ratio of the corresponding altitude also. So now again I can square each of these. I can say that since AB by DE is equal to BC by EF is equal to AC by DF, which is equal to AL by DM, I can square each of these. Since I can square them, I know area is nothing but square of these corresponding sides. So the area would also be equal to AL square by DM square. This is what we get. So ratio of areas of two similar triangles is equal to square of the ratios of the corresponding sides, or you can say that the ratio of areas of two similar triangles is equal to square of the corresponding ratio of corresponding altitude. So this is what you get, that the area of these two similar triangles is also equal to the ratio of square of the corresponding altitudes. So AL and DM are the altitudes here. So AL square by DM square. Now let's look at one of its applications. This is the Frank Lloyd Wright School of Architecture, which is in United States. You see that their main campus includes a triangular swimming pool. So there's a triangular swimming pool, and just along this triangular swimming pool you have a pathway. So what you can see is that these two triangles are nothing but similar triangles. The only difference is difference in size. In fact, this larger triangle has been scaled 2 times than this smaller inner triangle, which is the swimming pool. So let us draw a small diagram for this. So say this is what we have. A smaller triangle, which is the swimming pool, and triangle ABC, which is the pathway. I want to find the area of this pathway, which is ABC, also area of triangle DEF, which is the swimming pool. So I know that DE is 20 meters. I know EF is 21 meters. So there are two ways in which you can do it. I know that the larger triangle has been scaled by a factor of 2. So that means that each side is scaled by a factor of 2. So AB would be 2 times DE. Since side of the larger triangle is twice the side of the smaller triangle. So I know that the DE is 20. So I can say that AB would be 40. So you can say AB is 40 meters. These all measurements are in meters. So AB is 40 meters. Once you know AB, now I need to find area of this triangle. What would area of this triangle be? So area of triangle DEF. It's a right angle triangle. So one of the sides acts as base, one of the perpendicular sides is base, the other perpendicular side becomes the altitude or the height. So area of this triangle would be half into base into height. If I take DE as the base, then EF is the height, which is 21. So this is half into base is 20, which is DE, into height is 21. So I get area to be 210 meters square. So area of this swimming pool I know. I know that the side has been scaled by a factor of 2. So I know AB also. Now, what do you know about ratio of the areas? I want to find area of the larger triangle. So area of triangle ABC by ratio of the areas. So I get ratio of the areas. This is equal to square of the ratio of the sides. Ratio of side ABC. Take any side of ABC. Let's say AB, because we know AB is 40. So it would be AB square by a corresponding side in the other triangle, which is DE. So DE square. So this is what you get. Now you know area of triangle DEF is 210. You know AB, which is 40. You know DE is 20. So you can find area of triangle ABC. Let's find that. So area of triangle ABC would be AB square is 40 into 40 by DE square. DE is 20. 20 into 20. Area of this would be this multiplied by area of triangle DEF. So this is area of triangle ABC. This multiplied by area of triangle DEF, which is 210. Cancel the zeros. 2 2s are 4. So what I get is 210 into 4, which is 840 meters square. So this is the area of this larger triangle. Now subtracting the two, you can find the area of the pathway. That is what you wanted to find, area of this pathway. So area of pathway would be area of the larger triangle, which is 840, minus area of the smaller triangle, which is 210. So I get 630 meters square. So this is the area of the pathway which you had to find. Now, rather than following all this long way, let us try to find a shortcut to this. We know that if the sides are increased, sides have been scaled by a factor of 2, So area would increase by a factor of square of 2, which is 4. So what I need to do is find the area of the smaller triangle. The area of the larger triangle would be 4 times the area of the smaller triangle. So area of smaller triangle is, that is area of triangle, smaller triangle is DEF. This is half into base 20, height 21. Base into height. So this comes out to be 210 meters square. Once I know the area of the smaller triangle, area of the larger triangle would be 4 times the area of the smaller triangle. So area of triangle ABC would be 4 times 210, which is 840 meters square. Now you know the area of the larger triangle, you know the area of the smaller triangle. All you need to do is subtract the two to find the area of this pathway. So area of the path would be (840 square), area of larger minus area of the smaller. So I get 630 meters square. So this is what I get, area of the pathway as 630 meters square. So you can see how easy it is. If you know that the side is scaled by a factor, then the area would be scaled by a factor of square of that factor. Side increased by 2, area would be increased by square of 2. Side if it is increased by 3, area would be increased by square of 3, which is 9. So this is how we can use that ratio of areas of two similar triangles is equal to ratio of square of their corresponding sides, and it is also equal to the square of the ratio of the corresponding altitude.